Dear students, welcome to our online lecture series, and this is our first online lecture. So today we shall going to study the countability axiom. The countability axioms. Now the question is, what are the countability axioms? Now actually this is just a countable version of the following concepts. First of all, basis for a topological space, dense set, and compact set. And you have already studied all of this, right? Now in this chapter we shall see 4 types of topological spaces which satisfies countability axioms, and these topological spaces are the first countable, topological space, which is also related to the first countability axiom. The second one is the second countable topological space. Topological space, which is also related to the second countability axiom. That is, if a topological space is first countable, we shall say that that topological space satisfies the first countability axiom. Similarly, if a topological space is second countable, then we shall say that that topological space satisfies the second countable axiom. There are 2 more topological spaces. One is separable topological spaces, and another one is Lindelof topological space. Topological space. Now this one, that is first countable and the second countable, this is just a countable version of a basis, and this is that separable one is a countable version of the dense set, and this is a countable version of the compact set. So in this chapter we will going through all of this. So let's start with the first countable topological. Now before defining that first countable, we need another concept called a countable basis at a point x. So let x be a topological space and let x be a point in x. Now we say a countable collection beta x of neighborhood of x So what is the neighborhood of x? That's mean it is just a open sets containing x. So it is just a open sets containing x. Okay. So we say a countable collection of neighborhood of X is a countable basis at X if for every open set, or if for any open set U containing X, there exists a B, that is there exists an element from beta X such that X belongs to B subset of U. Okay, so now we are ready to define the first countability axiom. So the countability axiom. Okay, so let X be a topological space then the topological space X is said to be first countable if for each point X belongs to X, there exists a countable basis at X. That is, in other words, X is said to be first countable if for each X in X there exists a countable collection beta X of neighborhoods of X such that for any open set containing X, say that open set U, so for any open set U containing X, there exists an element B belongs to beta X such that X belongs to B subset of U. Okay, so if a topological space satisfies this property, then we will say the topological space is first countable, and in this case we say the topological space X satisfies the first countability axiom. Okay, now let's see some examples. So first one, let x equal to r, that is the real line with usual topology. Now it is easy to see that the topological space R with the usual topology is first countable. Why? Because let x belongs to R and let that countable collection beta x is just the open interval x minus 1 by n, comma x plus 1 by n, where n belongs to natural number. Now consider this collection. Now it is easy to see that for any open set U containing x, there exists a natural number n such that x minus 1 by n, comma x plus 1 by n, that is subset of U, right? And this is true for any x. So the topological space R with the usual topology is a first countable topological space. We can give another example, say RL, that is the lower limit topology. The lower limit topology. Again, let x belongs to R, that is here the topological space is R and the topology is the lower limit topology, right? Now for each x we can choose my beta x is just this one, right? Where n belongs to natural number. So the topological space RL is also first countable. In fact, it is easy to see that any matrix space is first countable. Why? Okay, we can see this one as well. So let XD be a matrix space so let x belongs to x, right? Now we can choose my beta x is just the collection all the ball centered at x and radius 1 by n when n belongs to natural number. Now this is a countable set of a neighborhoods of x, right? Now it is easy to see that then for any open set U containing x, there exists a natural number n such that x belongs to the ball centered at x with radius 1 by n subset of U. That's mean any matrix space is first countable. So we get 3 examples. First one is R with usual topology is first countable. Another one example is the lower limit topology RL is first countable. In fact, we prove that any matrix space is first countable. Now can you give me one example which is not first countable? Okay. Now one example is that is not first countable. This example is R with co-countable topology. Co-countable topology. So what is the co-countable topology? That's mean any set is open if and only if its complement is countable. That is, U subset of R is open if and only if R minus U is countable. Now just pause the video and try to prove that this is not a first countable topological space. Okay, now here I am giving the proof. Now suppose it is first countable. That is, let for a point X there exists a countable collection of open sets, that is a countable basis beta, and this is just Bn. N belongs to natural number. Okay. Now this is a countable basis at X means, or you can say at X. That is, for any open set U containing X, there exists one element from beta, say Bn belongs to beta, such that X belongs to Bn subset of U. Okay. Now it is given that each Bn is open. That's mean since each Bn is open, that is R minus Bn is countable. That is, B complement is countable. Now we claim intersection of all the Bn is also open. Why this is open? We have to show that its complement is countable. Now what is my R minus this? That is, B intersection of B complement is union R minus Bn this. Now we know that each of this is countable and it is the union of countable sets, so it is countable. Now since each R minus Bn is countable, so R minus intersection that Bn is countable. That will imply X belongs to intersection that Bn is open. Now again see that its complement, that is the complement of this set, the complement of this set is countable, right? That means this set is actually an uncountable set. So this also imply, so this also implies that this set is uncountable, right? Now choose Y belongs to Bn, that is intersection of Bn, such that y not equal to x. Since this set is uncountable and x belongs to Bn, right, intersection of Bn, so we can choose another element y which is belongs to this set and not equal to x, right? We can easily find such an point. Now let the set M equal to intersection of this minus that y. Now it is easy to see that x belongs to M and R minus M is countable. That is, M is open, right? That's mean M is an open set containing X, right? But Y belongs to Bn and Y does not belong to M. That will imply Bn is not subset of M for all n. So thus we get an open set M containing X which does not contain any open set or any neighborhood from beta. Thus, beta is not a countable basis at X. This is a contradiction. Therefore, the topological space R with co-countable topology is not first countable. Okay. Now we move to the second part of this talk, that is the second countable. That is second countability axiom. So let X be a topological space. We say that, or then X is said to be second countable if the topological space X has a countable basis. That is, there exists a countable collection beta of open sets such that for any element x belongs to x and for any open set U containing x there exists an element B from beta such that x belongs to B subset of U. That's mean if a topological space X has a countable basis, then we will say that the topological space is second countable. And in this case, the topological space X is said to be or is said to satisfy the second countability axiom. Now we shall see some examples. Now the first example is R with usual topology. Remember that we have already seen that the R, that is the topological space R with the usual topology, has a countable basis. So can you tell me what is the countable basis for the topological space R? So if we choose my beta equal to all of this collection, this open interval a comma b, where a comma b belongs to Q, that is the set of rational number, then so let beta equal to this, then beta forms a basis for the topological space R, right? And we also know that beta is countable because the first term a comes from the rational number, second term also comes from the rational number. So this collection has a cardinality maximum q cross q. And further, beta is countable as it has cardinality same as q cross q, right? So R with usual topology is second countable. Now another example is Rn, again with usual topology. Again, it is easy to give a basis for this Rn. Now, can you give me the basis? So, let beta equal to this one, that is a1, b1 cross a2, b2 product with an, bn. This product where ai, bi belongs to q. Now it is easy to see that beta is countable, right? Why? Because it has the cardinality same as q power 2n, right? Because here we have 2n number of elements and each of them comes from q. So it has the cardinality same as q cross q cross q up to 2n times, right? So beta is countable and beta forms a basis for Rn. That's mean the topological space Rn with usual topology, that is the product topology, is also a second countable topological space. Now there is another interesting example. Third one, R omega with product topology. Okay. Now we claim that R omega with product topology is a second countable topological space. So we have to construct one countable basis for this topological space. So first of all, let beta n equal to this one. So a1, b1 product with now an, bn, and then all of this are, and where ai, bi comes from q. Okay. Now let beta is same as union of n equal to 1 to infinity beta n. Now it is easy to see that beta is countable. Why? Because each beta n is countable as it has cardinality same as q cross q cross q 2n times, right? So beta n is countable and beta is countable. Why? Being an union, that is countable union of being a countable union of countable sets. Now we need to prove that beta is, that is, forms a basis for the topological space R omega with product topology. Now this is easy to prove actually. So first of all, okay, now claim beta forms a basis for R omega. So let x, which is my x1, x2, this belongs to R omega, and let U be an open set containing x. Okay. Now since x belongs to U and U is an open set, now there exists a basis element, this kind of basis element, say C1 D1 cross C2 D2 Cn Dn cross R such that X belongs to that set right, subset of U. Now we can choose rational number AI, BI such that CI less than AI less than X less than BI less than DI for all I equal to 1 to up to n. So it is better to write a different n, then there will be not a confusion. So let this is Cn comma Dn. Okay. So this is Cn Dn, right. Now that is, this implies so X belongs to that one. So A1 B1 product with A n Bn, this is R subset of U, right? So we have chosen one arbitrary point X and arbitrary open set U containing X, and we get one element from B, right? From this B. So this implies this B forms a basis for the topological space R omega. That is, so thus R omega with product topology is second countable. Right? Now what about R omega with box topology and R omega with uniform topology? Now we claim that, another example, R omega with box or uniform topology is not second countable. Okay, so we start with uniform topology. So consider R omega with uniform topology. Now we claim that R omega with uniform topology is not second countable. So first of all, we recall what is the uniform topology. So first of all, consider the metric D bar on R defined by D bar xi yi equal to minimum over mod of xi minus yi, 1. Now this forms a metric on R. Now if we define now rho bar x comma y equal to supremum over I d bar xi yi. Now this forms a metric on R omega. Now this topological space is called the uniform topology on R omega. Now this topological space on R omega is called R omega with uniform topology. Okay. Now we prove that R omega with uniform topology is not second countable. So let, if possible, there is a countable basis beta. Okay. Now let A be the set of all sequences of 0 and 1 in R omega. Now obviously A is uncountable, then A is uncountable, right? So we have three observations. The first one is R omega has uniform topology. Another one, we have assumed that R omega has a countable basis, say beta. And another one, we considered A, which is a collection of the all sequences with the entry 0 and 1, and this is uncountable, right? Now choose two elements. So let x, say which is xi, not equal to y, which is just yi, belongs to A. Now what do you mean by x not equal to y? That's mean, so there exists j such that xj not equal to yj, right? That's mean if x equal to 0, then xj equal to 0, then yj cannot be 0, that is it is 1. If xj is 1, that is yj is 0. So that's mean xj and yj equal to either 0 1 or 1 0. Now that implies d bar xj yj is equal to 1, right? This is our definition. See, their difference into 1 minimum, right? So this is 1. Now since this is 1, that will imply rho bar x comma 1 y, this is also 1. That's mean whenever we have two distinct elements from A, we always have their distance is 1, is exactly 1. Therefore, now let x belongs to the ball centered at x and of radius half. Now this is an open ball containing x, right? And it is given that beta forms a basis, right? So then there exists a Bx belongs to beta such that x belongs to Bx subset of B rho bar x comma half. Right? Now similarly, take y belongs to the ball of radius half centered at y, and there exists a by which is from beta such that y belongs to by subset of b half. Sorry, this is y. Right? Now note that if we take this ball, that is this ball, and if we take intersect with A, then it will be the singleton set X, right? Because we know if we choose any two element from A, their distance is 1. But here we have a ball X centered at half, right? So therefore, if we take this ball, that is Bx, that Bx will not contain any other element of A. That is A intersection Bx equal to singleton set X, and A intersect By is singleton set Y. And this is true for all X and Y. Now that will imply Bx not equal to By. Right? Now this implies the map F from A to beta, which sends an element X to Bx, is injective. Right? Why? Because whenever X not equal to Y, we have Bx not equal to By. So this is injective map. Now since A is uncountable, beta must be uncountable. Now this is the contradiction. Therefore, R omega with uniform topology is not second countable. Similarly, one can prove that R omega with box topology is also not second countable. So similarly, R omega with box topology is not second countable. One can prove that. How to prove? In this case, you can choose the ball x minus half x2 minus half this one. Choose this ball and you will get, and the remaining procedure will be the same, and you can get that R omega with box topology is not a second countable topological space. Now we have another interesting example, that is the long line. Now long line, this is also not second countable. So what is the long line? Long line is just a generalization of the real line. See, one can write that real line R as a union of n, n plus 1. That is, topologically, we take countable number of copies of line segment 0, 1 and we are just attaching them together. You can see here, so this is my 0, so we take 0, 1, right? We take another copies of 0, 1, so this is my 1, take another copies of 0, 1, this is my 2 in this way, and take another copies of 0, 1, this is my minus 1, 0, take another copies of 0, 1, minus 2, minus 1, so in this way, right? So we can consider R as a countable union of line segment 0, 1 and attaching them together, right? Now the long line is just a generalization of this. Now you take uncountable copies of this one and attaching them together. So roughly you will get so let X is the topological space R with the product with that 0, 1 and take the dictionary order topology. Right? That's mean you can consider this is my R cross 0, 1. Right? This. That is, we have this kind of line segments. So actually there is no gap, but to see the pictures I am giving this gap, but there is no gap between them, between any two line segments, right? Now we can it is easy to prove that topological space X, which is just a long line, is not second countable. The proof is same as the before. So in this case, take A equal to the collection X cross half, where X belongs to R. Now obviously A is uncountable, that is, it is just this kind of points. So this, the collection of these points, which is uncountable, right? Now for each point, X cross half, take a open ball B, that is open set, which is just X cross 0 to X cross 1. That is from this point to this. So for this point it is just this. If this is my X, so this is my ball, right? Now if possible, so suppose if possible there is a countable basis beta for X, right? Then each X cross subset of B, this ball, contains an element, say Bx belongs to beta, such that X cross half subset of Bx subset of B, right? Now if X not equal to Y, then Bx not equal to By, right? So that will imply the map F from A to beta, which sends X to Bx, is injective. Now that will imply beta must be uncountable. So that is, the long line is not second countable. Now these are the definitions of countable, first countable and second countable topological space. Now in the next lecture we shall see the separable topological space and the Lindelöf topological space, and we will see some important results.